So, good morning everyone. So, in today's lecture I am going to cover certain aspects of the solution of Euler-Lagrange equations, namely some of the aspects we have not covered so far yet. So, we have looked at the various cases or the various solutions of Euler-Lagrange equation for different case scenarios, but here are some of the issues that we have missed, namely the invariance issue, or what happens to the solution of the Euler-Lagrange equation when we change the coordinate system of our solution. So, how does Euler-Lagrange equation changes with a change in the coordinate system? So, that we will discuss in invariance, and regarding whether the solution even exists or not is going to be discussed in this second topic, and further we are going to generalize our Euler-Lagrange for more complicated problems, right. So, these are the three topics I am going to cover over this entire discourse of this lecture. So, let us start with the first topic, namely invariance, the invariance of Euler-Lagrange equations, right. So, as I said, invariance has everything to do with what happens to the Euler-Lagrange equation, how does it changes with a change in the coordinate system, let us say from Cartesian coordinate to polar coordinate and so on and so forth, right. So, the motivation of this discussion is as follows. We all know that any physical phenomena or any physical principle should not and does not depend on the coordinate system of our choice. So, if we were to represent any physical system which is occurring in nature as a mathematical equation, that equation should be independent of the coordinate frame we are working, whether it is polar, whether it is Cartesian, it should not matter, and which means that if we are solving an Euler-Lagrange equation for a physical phenomena, that Euler-Lagrange equation should also be independent of the coordinate system. So, the motivation of this discussion, as I just said, is as follows. So, what we have is that principles in physics that lead to variational formulations, principles in physics that lead to variational formulations, they do not depend on the coordinate system, right. So, what I just said is principles in physics, they do not depend on the coordinate system, that we have numerous examples. One example is the geodesics on a plane or the geodesic problem. So, the determination, for example, the determination of geodesic is frame independent, right, whether we want to find, and later on we will show that when we find the geodesic on a sphere, it is sometimes better to find the geodesic using a polar coordinate rather than a Cartesian coordinate frame, right, and we will see that the geodesic comes out to be identical, right. So, the determination of the geodesic or the optimal path is coordinate free, right. So, this is one case which we will see in depth later on. So, based on this motivation, one expects that the Euler-Lagrange equation should also be coordinate free, because many of these Euler-Lagrange equations, they describe the physical phenomena which are also coordinate free, right. So, one expects on physical or geometric background, one expects on physical or geometric basis that Euler-Lagrange equations are also coordinate invariant, right. So, this is the expectation, this is the intuition that is provided to us, and we will show that this is indeed the case in the form of a theorem later on. So, what I have just said is, if I were to find the Euler-Lagrange equation, let us say with respect to any frame u v, let us say variables u v which represents another coordinate frame, that should be the same Euler-Lagrange equation that we just described so far in the earlier lectures in the Cartesian coordinate frame, right. So, let us continue this discussion in a more rigorous fashion, right. So, let us look at a coordinate transformation. So, let us look at a coordinate transformation. A coordinate transformation where x is a function of u comma v and y is a function of u comma v, right. So, the coordinate transformation, this coordinate transformation is smooth. This coordinate transformation is smooth if there exists continuous partial derivatives, there exists continuous first partial derivatives with respect to u comma v, and we have a non-singular Jacobian. We have a non-singular Jacobian which is given by the evaluation of this following set of partial derivatives, which is nothing but the determinant of the following matrices, matrix x u, or the derivative of x with respect to u, y u, x v, y v, right. So, the Jacobian should not be 0. Only then we can guarantee that the transformation is smooth and orthogonal, right. So, that is what we assume. So, that is the underlying assumption, right. So, either this, we either denote the Jacobian by this or the determinant of this matrix, right. So, then let us look at a functional. So, let J be a functional, let J be a functional J of y, which is also equal to integral x 0 to x 1 f of x comma y prime dx, right. So, let me call this functional as my expression as 1, right, and let me further call this result, this assumption. So, this is all assume, this is assumption here, we call this assumption by assumption A, right, and let me describe the set S, my set S to be the set of all. So, let S to be the set of all second partial derivatives between the intervals x 0 to x 1 such that y of x 0 is y 0 and y of x 1 is y 1, right. So, we assume that, so this is the setup to describe the Euler-Lagrange equation in another coordinate frame u comma v. So, this is the basic assumption and this is the setup that we have. Now, further let us look at the other set of assumptions that we need. We further assume, so we have two coordinate frames, we have x y coordinate frame and we have the u v coordinate frame. So, we are trying to deduce the Euler-Lagrange equation in this frame, in the u v coordinate frame, given the Euler-Lagrange in the Cartesian frame, right. So, further we assume that v is a function of u, right. Why we do that? Because if this assumption is similar to the assumption that y is a function of x. So, y is the dependent variable which is dependent on the independent variable x, right. So we continue with the same assumption. So which means dy dx, the derivative of y with respect to x is dy du divided by dx du, which is also equal to yu plus yv v dot divided by xu plus xv v dot, right. All we have done is apply the chain rule, and that gives us the derivative of y with respect to x in terms of completely in terms of u and v, right. So let me continue. So which means my dx is nothing but dx du times du, or this is also equal to partial x partial u plus partial x partial v dot times du, right. So then it implies that my Jacobian 1 is identical to j of y, which is equal to the integral x naught to x1 f of x y y prime dx, right. Okay. So what we have is that this is also equal to the integral u naught to u1. So now we are going to substitute the different variables in the Cartesian frame in terms of the variables u and v. So namely my x is a function of u and v. So we directly apply the coordinate transformation rule. Instead of x, we use the rule x of u of v. Y is also a function of u and v, and my y dot or y prime, which is dy dx, is found out to be yu plus yv v dot divided by xu plus xv v dot. Okay. And then finally my dx is found here above, which is also equal to xu plus xv v dot times du, right. We also see that this integral is u0 to u1 f of u v v dot times du, right. So let me call this. So we have now finally reduced our functional completely in the form of the new coordinate system u and v. So let me call this as 1 prime. So this is the analog of the functional in the Cartesian frame, right. So then my new boundary conditions, we have to also change the boundary conditions, right. My new boundary conditions are x naught is equal to x of u naught v naught, and my x1 is x of u1 v1, and so I am directly using the coordinate transformation to figure out the boundary conditions in this case. And similarly my y naught is y of u naught v naught, and my y1 is y of u1 v1, right. So let us further redefine our set where the extremals are going to come from, that is the set S, right. So let my set S be redefined, right. So I am now redefining everything including the set. So redefined including the set S from the Cartesian frame to the uv frame. So my new set is the set T, which is equal to all v in C2 of x naught x1, such that v of u0 is v0 and v of u1 is v1, right. So we see that this new set T is now the set of newly defined functions which are second order differentiable with this new set of boundary conditions. Okay. So we are ready to describe the Euler-Lagrange equation, the equation in the new frame. So what we have is the following. We ask the following question. This question that motivates our discussion is the following. So if V in this new set T is an extremal Okay, let us go back a slide. Let me call this new extremal as k of v, right. So, I am calling this new extremal as k of v. My older extremal was defined as j of y, right. Okay. So, this question is, if v is an extremal of k, right, described in 1 prime, then is y in S an extremal of the set S, of the functional j and vice versa, right. So, v is an extremal of k, then is y an extremal of j and vice versa, right. So, we are going to answer this question in the form of a theorem, that the answer to this question is yes, right. So, the result in the form of a theorem is as follows, right. So, the theorem says, suppose y is in the set S and my function v is in the set T, be two functions that satisfy the smooth, two functions which satisfy the smooth non-singular transformation, A. A was the set of assumptions that we had here, A, okay. Smooth non-singular transformation A. Okay. Then y is an extremal. For j. Y is an extremal for j if and only if I have v is an extremal for k, right. So, the answer to this question above that I posed is yes via this theorem, right, and I am going to prove, the proof is very straightforward, right. So, suppose we assume one side, suppose we assume that v in k v in T is an extremal, for the functional k, then v must satisfy the Euler-Lagrange. So, v satisfies the Euler-Lagrange equation, right. So, what I have is d du del f del v dot minus del f del v is equal to 0, right. Okay. Okay. So, we see that this is the Euler-Lagrange being satisfied in this new coordinate frame. So, that is my assumption. Now, I know that my f let us go back a slide. Notice that my f here, this particular f is nothing but this whole quantity times this whole quantity. So, f is the product of small f of this argument times this particular quantity in this bracket, right. So, my f of u v dot is, I am just rewriting whatever I just said, is the product of this quantity yu plus y v dot divided by x u plus x v dot, right, times x u plus x v dot. So, that is my f. So, all I have to do now is to plug this f into this Euler-Lagrange and figure out all these partial derivatives in this boxed equation, right. So, let us do that step by step. So, So what I just said is the following. So del f del v dot is, so I am going to differentiate my f with respect to v dot, and we see that when we do that, let's go back a slide a bit. See that v dot appears here, which is a linear form with respect to v dot, and v dot also explicitly appears in this third argument of small f. So we need to differentiate these two arguments, these two quantities, right. So which means using chain rule, notice that this third argument of small f is nothing but y prime, the transformed y prime, right. So I can rewrite using chain rule that this is also equal to del f del y prime times derivative with respect to v dot, partial derivative of y prime, right. Y prime is yu plus yv v dot divided by xu plus xv v dot, right. So this is my y prime. So I have just used the chain rule, right, and times the factor that was remaining, right, plus then we differentiate this factor, we are only going to get xv times f, that we did not differentiate, that we differentiated earlier in this first case, right. So that is my del partial f partial v dot, right. Similarly, we can evaluate the other partial derivative del f del v, and we see that let us go back a slide to see where does v appears. Notice that v appears here, right. V also appears here in the second argument and also appears in the third argument, and also it appears here, right. So we need to differentiate with respect to each of the argument variables of f, and as well as this bracketed term, right. So my partial derivative of f with respect to v using chain rule is partial f partial x times xv plus partial f partial y times yv plus partial f partial y prime times partial v of the quantity, this quantity in the bracket, which is y prime, yu plus yv v dot divided by xu plus xv v dot, right. Okay. Times xu plus xv v dot, right. So that is the first term of the product rule, and then the second term of the product rule will be f times, we differentiate this quantity in the bracket with respect to v, we are going to get partial v of xu plus xv v dot, right. Okay. So then all we have to do is to substitute these expressions given by a and b in, so substitute a and b in, let us say, expression 1. Let us see we have defined expression 1 or not. So this is my expression 1, right. So we substitute a and b in expression 1, and then after all the simplifications we see that our equation reduces to the following form. So the original form of the equation was the following: minus partial v, and this is also equal to del x comma y partial uv times del x, right. Well, let me just change it to, it turns out that this is also equal to, after doing all the simplifications, after substitution of a and b, we get to the following stage where this quantity on the left of the Euler Lagrange reduces to the following quantity. This is also equal to del f del y prime minus del f del y, and students can all see that this quantity which I have bracketed is nothing but the Euler left hand side of Euler Lagrange equation in the Cartesian coordinate. So from here, let me call this as 2. So from 2 I will just say that theorem 4 follows. As simple as that, because if this quantity on the left hand side is 0, implies that only this quantity on the bracketed quantity on the right hand side will be 0, because the term, the Jacobian term can never be 0, otherwise the coordinate transformation will be singular, right. So, the Jacobian is non-zero. So, theorem 4 follows, right. So, which means that Euler-Lagrange equation is coordinate independent or coordinate free. So, that is a very good news. Let us look at an example.